start these talks by saying I'm a speech guy. So mostly what I'm interested in is how people interact using spoken language, and indeed how they would interact with artificial devices using spoken language. But I often find myself visiting PCT to understand some general principles of how these things would work in interaction. So what I want to do today is talk about something which I came across in doing some basic modeling, which is the notion of compliance, which, as I'll explain in a moment, is something very common in regular control systems, and has some nice implications, I think, in PCT, which I'm going to demonstrate to you, which includes conflict and cooperation, as you'll see in a moment. I need to. Right. Okay. So what is compliance? In fact, there's two definitions of compliance. The property of a material to undergo elastic deformation, which is the opposite of stiffness, and the act of conforming, acquiescing, or yielding. Now, the first one is interesting to PCT people especially, because that means the system is returning to its original state. So there's an attractor which is pulling the system back to its original situation, as opposed to this one, which is essentially saying something quite different, which is the act of, which is conforming to a new state, adopting a new state. So these are quite different things, even though it's the same word. And so I'm just trying to tease apart the difference here from the modeling perspective. So compliant systems which return to their own state, are essentially elastic. So a good example is a spring, and these systems are used in robotics, especially in an area called soft robotics, where you want a robot, which is typically a heavy metal, rather powerful piece of equipment. It has to deal with some material which would be damaged. And so soft materials are typically used. Compliant materials are often used. For example, on the right here, that's a gripper. So this is just elastic compliance, where using the natural properties of the material to facilitate some kind of control. Now, in robotics, compliance, that sort of compliance in the behaviour of the robots themselves, can come from two directions. There's some conventional looking industrial robots on the left, and something pretty weird, I'm sure you're thinking, on the right, pretty scary. Now the robot on the right, as you can probably see, is constructed from the sort of rubber bands and things like this. So it has a natural built-in compliance, much like any living system. So a lot of the construction material has elastic properties. But when it comes to a robot, the compliance actually has to be programmed in. And this is because of what's called back drivability, or indeed a lack of back drivability. So for a conventional robot, which has many gears taken from the motors to the movement, if you attempt to physically move the end effector with your hand, you won't be able to do it because the impedance is huge. But it can be programmed, so the robot can be made to exhibit compliance, even though the materials it's constructed from don't have it. So that's a very interesting contrast between essentially a living system's capabilities and the non-living system. So I'll just throw this up, of course, the classic PCT control loop, there it is. But I like to, sorry, yes, and the stiffness, which is one of the aspects of compliance that I'm talking about, is essentially in the loop gain, which is, if you've been looking at the chat, you'll see there's a lot of talk about loop gain. And so the higher the loop gain, the stiffer, the greater the control, the stiffer the system. The lower the loop gain, the looser the control, the less stiff the control. And compliance of the first type is inversely proportional to that. It's inversely proportional to stiffness, as we said. Now, I like to look at these kinds of diagrams, which are straight out of control engineering. It's the same idea, exactly the same as PCT. It's just that it gives me room on the left to do some stuff. So here we have the controller again with the loop gain and the stiffness as before. And of course, as we know, the error signal is key here, and that's going to be reduced by adapting the feedback signal. In other words, the control loop is going to operate to achieve control by reducing the error signal. But it also, you can reduce the error signal by adapting the reference, changing the intention of the system. And that's really what I want to get to here, the second type of compliance. So we can add a second layer of control. And so you can see another error signal there and another controller, this time defining the reference for the first system. That second layer of control also has a reference, which you'll notice is coming from the same place. Now, if you're paying attention at this point, you'll notice that the two error signals are actually, apart from a sign, are essentially the same thing, which means that we can collapse this. So the two loop gains, the first one is the stiffness, the second one is the compliance of the second type. But because the errors are essentially similar, we can just do that. So that's exactly equivalent. We just inverted a sign. And we're taking the error signal back into the reference, and then we have control using the compliance loop gain over the degree to which the reference for the first system is going to adapt. In other words, be plastic, be elastic, if you like. Okay, so now I want to add an additional layer here, which brings me back to my own interests. And as I say, I'm a speech guy, and I'm also interested in how behavior impacts on affective reactions and emotions, stuff like this, in a very simple way. And I, again, like to use PCT as a means for expressing these ideas in a very simple and easy to digest way. So here's the control system, but now I'm going to talk in terms of more psychological variables. So that is the original intention of this structure. The loop gain here, I'm going to call motivational efforts. It's the degree to which the system or the agent now is, somebody else has got the microphone on. The degree to which the agent is cares about control. So that is the loop gain, but I'm giving it this psychological label, and we can call that arousal if you're in the effective terminology. There's the motor command, the action. By the way, the red labels here refer to things that variables in the simulation that's coming up that are under control, under my control as a designer. So there's the action. Then there's the tension, the degree of effort that is put into perception, which is an important aspect of the story here. Is the perceptual signal, if you like, it's the consequences of the control. Then there's an appraisal mechanism. This is terminology from affective science. There's an appraisal, and the error effectively is the emotional valence. In other words, low error is good equals happy, high error equals bad equals unhappy for this agent. Back here we've got more effort. This is the motivation to comply. So the degree of adaptation is also a motivational parameter, and it's the degree to which the agent is willing to adapt its intentions based on experiences that it's having. Okay, so that's the kind of the background, and now I'm going to just basically show you a few demonstrations. And they're all within this environment. So if you've seen me talk before, you know I like this pure data programming language. It's very nice. Real-time visual programming language. It's particularly designed for audio, which means I can do all kinds of speech-related things, but that's not the important point here. This is the main panel, and I'll just talk you through this because you're going to see this operating in a moment. So over on the left here, we've got an environment. And the environment's very, very simple. it contains stuff, and the amount of stuff is fixed, but the stuff can be either on to the left or to the right. And it's possible to move the stuff around, either manually, or as we'll see, the agents can move the stuff around. And the agents can move the stuff from left to right or from right to left. So that's what that's all about. It's just a very, very simple environment. In other words, it's a variable which we might want to have under control. There's a graph here, which is essentially going to be a timeline, which shows you the amount of stuff that's on the left. So in other words, if all the stuff is on the left, then that graph will be high. And if all the stuff is on the right, then that graph will be low. It's just a parameter that's being controlled. That's all we talk about. Here we've got three different types of potential disturbance, which can be switched on or off. There's a manual disturbance, which means that if you vary that blue slider manually, you can intervene like God, if you like, in the environment and change the amount where the stuff is. There's a noise disturbance, which you can see there's a rate slider there, so you can control the amount of noise that's disturbing the environment. And there's a ramp. All will become clear in a minute when you see this working. Over here, we've got a couple of agents. So this is one agent, and it's capable of moving stuff from right to left or left to right in the environment. It looks a bit complicated, but there are various sliders there. You've got the intentions, which are matched in color with the environment, so that you know that's related. Then there are a couple of other controls. Here's the motor effort and the perceptual effort, in other words, attention. Now, what's important in all of this is that these are implemented not as gains on the control loop, but they're implemented as sampling rates. It doesn't matter too much, but it's an interesting perspective on the degree of effort that's put into control. If you think about it from the attention point of view, it's like how often you look is going to matter. And the more attention you pay to something, the more information you'll have to control. And on the right-hand side, you'll notice there's a happy, sad indicator that is directly linked into the error signal for the lowest level control. Okay, so I've now got a bunch of demos to give you, and we'll start with something really simple. I just did my cheat sheet to make sure I'm describing this properly. So what you're just about to see is essentially, I don't know if you can see my mouse, yes. I think you're going to see this being moved. No, sorry, no, you're not. Right, back to my cheat sheet. Right, you're going to see me clicking on these two buttons here and just manually moving stuff around, and you'll see that reflected in the graph below. And there we go. These are all pre-recorded videos just to make sure there's no slip-ups. So hopefully you're seeing that, and you can see me clicking, moving stuff around. So let's just make sure you can understand what the environment is. Very straightforward. Okay, so that's moving stuff around manually. So let's have an agent moving the stuff around now. The important thing is there's no disturbance. But what I want you to pay attention to is the attention and effort controls, which will be varied. So what you'll see at the moment is that the intention of the agent is different to what the reality in the environment. So initially, it's going to be not very happy. And then as the environment is brought under control, the error reduces, it will get happy. And so keep an eye on the right-hand side. So that's the agent now starting, not very happy. And it basically, you notice that I'm varying the intention, and there's rather slow adaptation. The control is slow, and that's because the effort and the attention are sort of medium level. Now I'm going to put up the attention. There we go. And that doesn't actually make a big difference, because it's, of course, it's the motor effort that is going to impact on the speed of control. So now we're going to increase the motor effort. And if you look at the graph, now you're seeing very, very fast reactions. So that, if you like, you can think of it as the loop gain, but it is actually just the sampling thing. Now I'm going to reduce the attention. So I've got full effort, but I'm not paying full attention. And the consequence now is we're getting oscillations, because it's, in other words, this agent is working hard to achieve control, but it's not paying enough attention to what it's doing. And so there are delays now, and so there's oscillation in the environment. And if you were noticed on the right-hand side, it was therefore not happy quite a lot of the time. Okay, so hopefully you're with me. There are 9 of these. Right, so now we're going to put in a disturbance. This is going to be noise, so the middle one. And initially, there's going to be no control at all. And then going to increase the attention and effort and show that it brings the environment under control. So that's starting the noise at a modest level, but I'm going to put it up to maximum. Here we go. So that's a noisy environment. That's the wind blowing, if you want blowing the stuff around. And initially, with a medium level of effort, medium level of attention, there is not much control. The error is high, the agent is sad. And we put up the attention and effort, and that noise is now moderated somewhat. It's under control. Okay, so this is all this is all standard stuff. I'm just making sure you understand the basics here before we get to the compliant thing. Okay, and I switched the agent off, just shows that all that noise was going on in the background. So I mentioned there are 3 types of disturbance: manual, noise, and a ramp. And the ramp is quite a fun one. So this is just demonstrating control over the ramp with sufficient effort and attention. So here's the ramp. So this is a bit like Rick's had a sine wave. I've just got a triangular wave as a disturbance. Here's the agent. And we're going to essentially just put the attention and effort to full. And then that shows we have perfect control. And it's very fast control because it's putting in maximum effort and it's paying full attention to what it's doing. So obviously it gets a little bit unhappy as its intentions change, but then it brings the environment under control. Now I just switched the agent off, and you can see that that's ramp was still going on in the background. Right, so now let's turn to compliance. So remember when I described the compliant aspect, this is now the second layer control, which is capable of adapting to the error and adapting in other words, changing the reference of the lowest level in order to reduce the error rather than controlling it. So this is what you're going to see now. It's going to be with that ramp, and you're going to see the compliance, which is currently at minimum, will go up to maximum, and you will see that the agent will be compliant with the disturbance in this case, and nevertheless is going to be quite happy because the error, of course, is low. So here's the big ramp. And start the agent, put up the attention and the effort. Oh, no, I'm leaving effort in the middle. Right. Okay. No. Right. That's right. Yes. Okay. So what you're about to see there is there was some adaptation in the second controller. And so the ramp is now very visible in the environment, and the agent loves it because the agent is now essentially tracking the disturbance. The agent is being driven by the disturbance because it is complying. It's completely 100% compliant. Okay, so now we get to touch on some of the things that Steve was just asking about and links into Rick's talk. So we've got 2 agents now on the right-hand side. And they have the same intentions right now, but you'll notice that the efforts are not at maximum. The motor effort is not at maximum, and the ramp is going to be the main disturbance. And what you're going to see first is that because the motor efforts are not at maximum, neither agent individually has control. But then I will switch on both agents, and their combined efforts will be sufficient to bring it under control. The very definition of cooperation. So there we go. So there's the ramp. There's no agents operating at the moment. So that's the first agent. You can see that it's trying to control. It's not succeeding. It's not very happy. I switched it off. Switching on the second one. So this is only the second one operating, exactly the same. It has a very poor control. It's not very happy. Now we bring in both agents, and the combined efforts of both agents brings it under control, and they're both reasonably happy. So that is a demonstration of the cooperation. Now we're going to have two agents with different intentions. So this is going to be conflict. And right, to start with, you'll notice that the first agent, the one at the top, this one here, has a higher level of motor effort than this one. So what psychologically you say, this one cares more about keeping the environment under control than this one does. Right, let me just run it. So here we go. So basically what this is demonstrating is that that first one has control because it cares more. The second one has no control whatsoever because it's not putting enough effort. Remember, they have different intentions. So if the second one now I put in more effort than the second one, it has taken over control because it's basically trying harder now. So it has control, and the other one has lost control. So now the number two is happy, and the number one is sad. Good. All right. So now we're going to get to a couple of final ones on compliance. So we've got two agents with different intentions. Okay, so potential for conflict, but there are going to be differences in compliance. So I'll talk you through this as it happens. So that second agent, you notice, is currently in control. It's got a higher degree of motor effort. First agent doesn't really have control at all. Now I'm going to increase the compliance of the second agent. The second agent is now completely subservient to the first agent. This is independent now of the disturbance. The disturbance is under control, but that second agent is now basically compliant to the first. And in fact, look, I'm trying to change the intentions of that second agent, and it's constantly being brought back by that second loop because it's compliant to the first agent. It's now a subservient agent. Okay, and then finally, with all that conflict going on, let's have some compromise. So what we've got now, two agents with matching efforts, more or less matching intentions, and they're both compliant. So they're both going to be adapting to the situation that's taking place in the environment. By the way, when I said they were adapting to each other just now, I should have been clearer. They're only seeing each other through what's happening in the environment. That's probably a rather important thing to say. Okay, so here we go again. And what we have now is these two agents. There's still a ramp in the environment behind the scenes. And you'll notice that we can just about change the intentions of one of the agents, but it's brought back by a combination of what's going on in the environment, which is the disturbance, plus what the other agent is doing in the environment. So they're kind of compromising agreeing between themselves what the joint intention should be, and always just manipulating various values on these different controls. So what? I hear you say. So compliance, I've been using these terms adaptations. This is a form of learning, if you like. Indeed, there's some aspects of mimicry here. And another way of looking at this is actually it could be just construed as recognition of intents from another agent. Basically, the compliant agent is learning the hidden parameter of the dominant agent and effectively has become that other agent. I've now got a model of the other agent. And it's essentially a generative model of perception, pretty much as in predictive processing. And in my field, we often talk about things like recognition by synthesis, which is a special case of understanding by doing. Same idea as mirror neurons. And it's essentially a simple explanation of how those properties can emerge from very simple control parameters. Bottom line is that complying is a form, can be construed as a form of explaining what's going on. And then having imported that structure, the agent then can make use of it for quite other purposes, perhaps. Okay, so I'm going to finish there. Basically, the main points were natural living systems are intrinsically compliant, but engineering systems are typically stiff. So that means that engineered systems, we've got to do something explicitly to make sure that they exhibit some form of compliance. PCT is a very good way of thinking about all this, but it offers us these two views of compliance, which is rather nice. And the simulations I've showed you hopefully have illustrated a sort of wide range of different behaviours using only a few parameters, but embedded within the PCT framework is a very nice way of looking at things, and particularly interesting what happens when you have matched and mismatched compliances. And then the last point was the link between what's going on here in terms of adaptation and more interesting and general forms of generative model learning. And that's where I want to finish. Thank you very much. Oh yeah, sorry, just if you want to find out a bit more about compliant control, there's a paper there. And actually all that software is on my GitHub if you want to download it and play with it. But that's the end. Thanks a lot.
Thank you a lot, Roger. I am a pure data fan also.
Oh, wow. Finally.
Yes, so much fun. I love it. Do we have any questions for Roger? I guess Trinley has written something in the chat.
You see a hand of Gary.
Ah, okay, Gary. Yeah. Go on, Gary, please. I guess
no, but you're very, very quiet.
You can hear me, right? Okay.
Just.
Oh,
yes, there
I
is
have my
no...
mic in the wrong spot. Okay, yeah, that should be better. So, as I understand the control systems, you know, the different components are receiving information that's right there, right? I mean, it's not, the basic systems don't do any type of prediction whatsoever. So now you're talking about predictive perception or predictive processing, and I'm trying to understand exactly what that means.
No.
The system is. Go
I
ahead.
wasn't demonstrating predictive systems. I was simply pointing out that a system which is compliant, which has therefore taken on board the control structures of another agent, is then in a position to use those control structures in a predictive way. So I didn't demonstrate that at all. I was merely extrapolating from where we ended up. Because it's adaptive, it means that it has essentially learned something about the other agent. It knows what the other, in other words, it's done, you can think of it as an intent recognition, but it's an intent recognition by being able to generate that very behavior itself.
Okay, so in an interpersonal way, that if I know that my wife doesn't like loud music and I put it as I would like to hear it, I can predict that she will protest, and so I will reduce my volume even before. Is
For
that
example,
sort of
yes.
compliant?
Or more, yes, or more directly, if she went and turned it down, you would know why.
Yeah, okay. Okay, I can understand that.
Yeah.
Thank you.
Very interesting. Well, can we move on to